In this lesson, we'll look at different methods of solving quadratic equations, and then we'll learn completing the square procedure. A quadratic equation is any equation that can be written in the form ax squared plus bx plus c equals 0. Those coefficients a, b, c are real numbers, and in order to make sure that we really deal with quadratic trinomial on the left-hand side, we assume that the coefficient a is different than 0. This form of quadratic equation is called standard or general. Those names are often used interchangeably. So what are the methods of solving quadratic equations? The very first one, probably the easiest, although not always very exact, is solving by graphing. Let's take an example. To find solutions of the quadratic equation x squared minus 4 equals 0, what we do, we can graph the function x squared minus 4 and then look at x-intercepts of that function. So the places where the graph crosses the x-axis are the roots of the original equation. Let's graph it. We can check a few points. For example, what's f of 0? Well, that's 0 minus 4, so it's negative 4. Therefore, we plot point 0, negative 4. 0, negative 4 is exactly here. Okay, this point belongs to the graph of our function f. Well, let's check a couple more points. F of 1, that's 1 squared minus 4, which is equal negative 3. Notice that if we try to evaluate this function at negative 1, the answer will be exactly the same, because negative 1 squared is also 1 minus 4, which gives us negative 3. So we already have 2 points, very symmetrical points, 1, negative 3, and negative 1, negative 3. Let's plot them. That's 1 point, and that's the other point, right? Negative 1, 1, and this is negative 3. So far we have these 3 points to join. Let's try one more. F of 2, which will be exactly the same as f of negative 2, since we are squaring the 2 or negative 2, and that gives us the result 4. 4 minus 4 is 0. So overall, f of 2 is 0 and f of negative 2 is 0. Let's plot it. It will be here and there, 2 and negative 2. And now we can join those points. The result is a nice parabola like this. So the x-intercepts are negative 2 and 2. Therefore, the solution set of the original equation consists of negative 2 and 2. So in this particular case, we could easily read the x-intercepts from the graph. But our original equation was a very specific one. It didn't even contain the middle term, bx. Generally, if we have any quadratic trinomial, the graph of it can cross x-axis in any real number, so it might be impossible to read the exact roots directly from the graph. So that's why graphing method is not always precise. However, it gives us some intuition where to look for the roots. What are some other methods of solving quadratic equations? Well, the next one is solving by factoring. Let's consider the same example, x squared minus 4 equals 0. We can solve it by factoring the left-hand side. This is actually difference of squares, so it factors into x plus 2 and x minus 2 equals 0. Therefore, we can rate the solutions from each bracket. Each bracket contributes to one solution. We're using the zero product property. The product of two factors is 0 if either the first factor is 0 or the second is 0. Well, the first bracket is 0 when x is negative 2. The second bracket is 0 when x is 2. So again, we've got the same solutions. The following method of solving the same type of equation is square root property. How does it work? Well, since we want to solve for x, let's leave the term involving x on one side of the equation and move the free term to the other side. But this strategy works only when we have just one term involving x. Okay, let's move the 4 to the other side. We apply square root to both sides. Square root of x squared is equal to absolute value of x, and square root of 4 is 2. Now, this absolute value equation gives us two possibilities, x equals to 2 or x equals to -2. So our solution set is as before, -2 and 2. But what if we need to solve quadratic equation with all three terms? Well, sometimes if the left-hand side is factorable, we can still use factoring strategies, right? However, in this particular case, the left-hand side is not factorable. So how else can we solve it? Well, maybe we could use square root property as before. But remember, in order to use this strategy, we need to have only one variable term, not two terms like in our case, right? So the idea is to look at these first two terms and try to complete them to the perfect square. So we will be able to fold it back to the square of something in a bracket. Okay, to make it easier for us to focus on just these first two terms, let's bring the free term to the other side of the equation. And now let's recall, how does the perfect square work? Well, the perfect square of a plus b is a squared plus 2ab plus b squared, right? Observe that what we have so far is the first two terms, x squared and 6x. How can we connect what we have on the left-hand side of the equation with our formula? Well, it seems like x plays the role of a. That's our first term, right? So instead of a, we have x squared, and then it's plus 2 times a, which is x, times b that we don't know yet. So let's keep it b, and plus the last term b squared. Our goal is to find out b. Our goal is to find such b that we could fold it back to x plus the unknown b. I will leave the space for b. Okay? How can we figure out what the b is? Well, we need to look at the middle term, 6x. This needs to match the middle term of our formula. Therefore, let's compare these two terms. Our 6x has to match 2xb. Obviously, the x can be reduced because it's the same on both sides. So how do we come up with b? Well, we basically divide 6 by 2, which is 3. So what we did, we took half of this middle coefficient. Since we already know what b is, let's replace it here. b is actually 3. So here's 3 squared, and in the bracket we have x plus 3 squared. That means that our first two terms, x squared and 6x, are the part of the perfect square formula if only we add perfect square of the b in the end, which is square of the 3. Okay, so let's add 9 to both sides of our equation. That gives us x squared plus 6x plus 9. This falls back to the perfect square expression. It's perfect square of x plus 3. And obviously, since we added 9 to the left-hand side of the equation, in order to keep our equation equivalent to the previous one, we have to add the same 9 to the right-hand side of the equation. Let's look at it again. How did we come up with this number? We took half of the middle coefficient, which in our example turned out to be 3, and then we squared it, because the perfect square formula calls for squaring the b, right? So half of the middle coefficient and square it. That's our number. So we complete the square by adding perfect square of half of the middle coefficient to both sides of the equation. That's one approach. The other approach would be like this. Let's look again at our second equation. We can rewrite it without doing this step directly here. We can top up the left-hand side of the equation to the perfect square of. So we prepare a bracket, square it, and in the bracket we write the same x, the same sign, in this case plus, and we write exactly half of the middle coefficient, which in this case is 3. After squaring, since this perfect square of binomial consists of 3 terms, it is x squared, it is 6x, and it's also plus 9. So it's really larger than our previous expression by 9. Therefore, we need to subtract this 9 in order to make sure that our left-hand side is equivalent to the previous left-hand side. And after this step, we just copy the rest. Therefore, it's equal to 4. So again, this rule works as follows. Take half of the middle coefficient, square it, and then subtract perfect square of the number that you took. So you can complete the square using this method or using that method. Either one is fine. Personally, I prefer the second one, but quite often in textbooks you will find the first one. Notice that both of these methods are equivalent, since in this line the first three terms fold back into the perfect square as in the second line, and if we move this 9 to the left-hand side as -9, you can observe that these two equations are equivalent. If you look at these three terms on the left-hand side, they constitute a perfect square of x plus 3, right? So that's the same as the bracket square here. And then the 4 is the same. So the only difference between the two equations is that in the top equation we have plus 9 on the right-hand side, and in the bottom equation you have -9 on the left-hand side. Obviously, this movement is equivalent. Therefore, no matter which way we write the completing the square procedure, we end up with perfect square of something equals to 13. So now we can use square root strategy. Let's take square root of both sides of this equation, which gives us on the left-hand side absolute value of x plus 3, and on the right-hand side square root of 13. Instead of writing this absolute value, we can write directly x plus 3. However, we need to remember to use plus or minus root 13 on the other side, right? Those are the two cases that absolute value results in. And finally, to solve for x, we move the 3 to the other side, so it becomes -3 plus or minus root 13, which means our solution set consists of two roots, -3 plus root 13 and -3 minus root 13. So that's how completing the square procedure works. Let's practice solving equations by completing the square. In the first example, we already have the perfect square of something equals to a free number. So we are ready to apply square root on both sides, and then square root cancels the square. However, the answer is dual. The left-hand side is equal to plus or minus root 10. Don't forget the plus-minus possibility. And now to finish the question, we just need to solve this linear equation. So move the 5 over, -5 plus minus root 10, and divide by 2. So x by itself is -5 plus or minus root 10 over 2. Those are the two possible answers. In the second example, we don't have the perfect square. We have two terms with x's. So here we need to complete the square. How do we do it again? Prepare a bracket that will be our future perfect square of what? Of x minus, and then half of the middle coefficient, so 7/2. Quite often we'll deal with fractions here. Then, since this perfect square is larger, it contains three terms when unfolded, right? So it's more than whatever we had. Therefore, we need to subtract the last term of this perfect square formula. And the last term is perfect square of this number. So perfect square of 7/2 is 49/4. This way, we didn't change the left-hand side. It's exactly the same. And then copy the rest equals 10. Next step, let's move the free number to the right. So we have x minus 7/2 square equals, since it would be nice to prepare the ground to add these two fractions, instead of 10, let's write 40/4. Change to the denominator 4. And then we add 49/4. So altogether is 89/4 on this side. Now we're ready to take square root on both sides, which leaves us with x minus 7/2 on the left, and here it's root of 89. root of 89, let's stay with it, over root of 4 is 2. However, remember that we end up with plus or minus because we didn't write absolute value here. So we're nearly done. The final answer is x equals, let's bring the 7/2 to the right hand side, that becomes plus 7/2, right? And since both fractions have the same denominator, let's leave the answer with common denominator 2. That will be 7 plus or minus root of 89. Here it is. The following example is nearly the same as example B, but we have fractional coefficients. Okay, let's follow the procedure again. Prepare a bracket. We are squaring r plus half of this middle coefficient. How much is half of 2/5? Well, it's 1/5, right? And then we subtract perfect square of the number that we took in the bracket. So it's 1 over 25. Copy the rest, equals 4/5. Next step, let's bring the free number to the right. So r plus 1/5 square equals, and let's bring the 4/5 to the denominator 25. So 4/5 is how many 25th? 4 times 5, 20. And then it's plus 1 from that side, right? So altogether 21 25th. Okay, now take square root on both sides. We end up with r plus 1/5 equals, it will have to be plus minus, right? Because we didn't write absolute value here. And then it's root of 21, let's stay with it, over root of 25 is just 5. Notice that in both cases, here and there, we end up with fractions with the same denominator. So it's nice because we can add them easily, right? Let's keep this common denominator 5 and then bring the positive 1 to the other side to make it -1, plus minus root of 21. That's our final answer. We'll see soon that this common denominator is not a coincidence. We will always deal with the same denominator in the end. Let's see the last example. How this example differs from the previous two. Well, we have leading coefficient 2. Previously, to complete the square, we always kept the leading coefficient 1. Okay, since we don't want to have any extra problems, let's bring this form to the previous forms, to leading coefficient 1. How? By dividing the whole equation by 2. We want to get rid of this leading coefficient, right? So we end up with the leading coefficient 1. However, we'll create some fractional coefficients in other terms. So here we have 3/2 x and minus 1/2 equals 0. From now on, let's do exactly the same as in example C. So let's consider the first two terms. We're going to complete the square only of these two terms. In the meantime, bring the -1/2 to the other side. So here we'll have bracket, square, x, the same sign, half of this middle coefficient, so it's 3/4. If you divide a fraction by 2, the 2 goes into denominator, so it makes it 4. And then we subtract the extra, we subtract the part that makes this expression bigger than the original one, meaning the third term, which is 3/4 square. So subtract this number square, which is 9/16. Notice that after squaring the bracket, we always subtract, right? In all cases, we subtract. So this last sign doesn't depend on the sign that is in the bracket. We will always subtract perfect square of the number that we took in the bracket. Carry on. The 1/2 could be written on the right as a positive 1/2. And now we know what to do. Bring the 9/16 to the right, combine it with 1/2. So we'll have x plus 3/4 square equals, if we change 1/2 to the 16th, the 1 becomes 8, and the -9 becomes +9. Now we're ready to take square root on both sides. So here we have x plus 3/4. Over there, remember, two possibilities, plus or minus. and then is square root of 17 over square root of 16, which is 4. Finally, x is equal, with common denominator 4, let's move this positive 3 to the left. It will become negative 3 plus minus root 17, and we're happy. We've done. And the very last method, it's called quadratic formula. We can solve any equation. It doesn't have to be factorable, doesn't have to have nice coefficients, can be any quadratic equation. We can always solve it by using quadratic formula. That's this formula that is on the left-hand side here, where a, b, and c are the names of numerical coefficients of quadratic equation in decreasing order of exponents. So our a in this case is 3, our b is positive 2, and our c is negative 5. Sometimes I tend to use sub-indexes for the x to indicate that we are talking about two roots. So x1 and x2. x1 is with one sign, x2 is with the other sign, because the formula contains this dual sign. One possibility is with plus, the other with minus. We usually end up with two roots. This formula didn't came from the heaven. It was actually derived from the general quadratic equation by applying completing the square procedure. And we are going to derive it in the next video. For now, we just need to be able to use it. Okay, so here's the example. We have our a, b, and c. Let's plug it into the formula and simplify according to order of operations. Our two possible roots are negative b, since b is 2, we have negative 2, plus minus square root of b squared, which is 2 squared, minus from the formula 4 times a, but a is 3, times c, which is negative 5. Everything over, and here a little remark, don't be sloppy when drawing this division bar. It has to go over everything, not just the root or under the root. It is over everything together with the negative b. 2 times a, so 2 from the formula and a is 3. That's how we plug in information to our formula, and now we just simplify it. So we have negative 2 plus minus square root of 2 squared is 4. These two negatives, when multiplied, gives us positive, and then 4 times 3 times 5, oh, that's 60, right? 20 times 3, it's 60, over, and here's 6. Okay, so we have negative 2 plus or minus root of 64 over 6 equals, we can simplify this root, so we end up with negative 2 plus minus 8 over 6. In this case, we can combine the two numbers, so let's do it. However, because of these two signs, we need to write two different answers, right? So maybe let's place a bracket like this and write one answer in the top and the other answer in the bottom, right? So negative 2 plus 8 would be 6 over 6, which is 1. And then negative 2 minus 8 is negative 10 over 6, which is negative 5/3 after simplifying. Therefore, our final answer is x is either 1 or negative 5/3.